Welcome to Embedded Edge, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on embedded systems, technologies and products, featured on embedded.com and through other Aspen Core media publications. In this show, you'll hear both engineers and executives discuss news, challenges, and opportunities for embedded systems design in markets such as automotive, industrial, aerospace, and consumer. Here is your host, Editor-in-Chief of PowerElectronicsNews.com and Embedded.com, Maurizio Di Paolo Emilio.
Hello everyone, and welcome to this new episode of Embedded Edge. Today we will talk from silicon to light, a journey to smarter, greener AI. So we will talk about photonic computing. Our guest is Michael Förtsch, CEO of Q.ANT, a pioneering company at the forefront of photonic computing. As industries continue to seek more energy-efficient solutions to meet the demands of AI and high-performance computing, Q.ANT is reshaping the landscape with its photonic native processing unit, NPU. With a focus on using light instead of electricity, Q.ANT innovation promises not just higher computational density, but also a reduction in terms of energy consumption. So today we will dive into the fundamental differences between traditional silicon-based systems and photonic computing, but also the potential of thin film lithium niobate in this revolution, and the broader impact on industries beyond AI. Michael will also share his vision for the future of photonic computing and how it may soon integrate into our current infrastructures, and sharing in a new era of greener technology. So let's talk with Michael. Hi Michael, thanks a lot for being here. How are you?
Pretty good. It's Thursday and almost sunny here in Germany.
So where are you located in Germany, Michael?
We are located in Stuttgart, which probably everyone knows in the world, right? It's in the Baden-Württemberg.
Good. So, Michael, let's start with this topic. As I mentioned at the beginning, let's start with the basics. So, could you explain the fundamental differences between traditional silicon-based computing and photonic computing? So, how does the computational density of photonic processors compared to traditional ones? Traditional ones, I mean CMOS processors. So what advantages does this offer for high-performance computing tasks?
Thanks. Yeah. So before we look into the photonic processor, let me quickly remind ourselves of the classical ones. So the fundamental element, and this is important to understand, of classical processor is a transistor, or frankly speaking, an electrical switch. So it's either on or off, representing a 0 and a 1. And logic comes from this because we are using this fundamental so-called binary encoding. Now, engineers have defined 4 substantial gates based on this binary encoding. And what you can say is that these gates then already rely on more than one transistor, right? It's always a group of transistors representing a gate. And from these gates, we can then basically represent multiple mathematical functions or algorithms. Now, the key message is that regardless what in the end we want to compute, it's going to be broken down on the binary computer, so 0 or 1. This is already the major difference, because a photonic computer, you can consider it inherently as an analog computing device. So it's not just 0 or 1, but it can be anything in between, as it's a propagating wave. And this is the big difference. And for instance, by combining 2 of these propagating waves, you can already create a new mathematical function. And this is, in the end, the major difference to the digital world. Now, you already addressed a very fundamental question: which one is better, or which one has the better compute density? And to understand this, the fundamental calculation power of a transistor, so classical-based processor, comes from, in the end, of the number of transistors in a total on a certain area. This is what we refer to as compute density. And to give you some numbers, the state-of-the-art CPUs, for instance, have 100 billion of those transistors. And if you look on the GPUs, on the latest ones, they have even twice as much, so 200 billion transistors on one chip. So the key question is, how many transistors do you need for a dedicated mathematical function? If we, for instance, carry out a multiplication, we need around about 1,200 of these transistors to carry out a multiplication. So 2 times 3, 1,000 transistors on average. Extracting a root is already 7,000 transistors. And if you want to calculate the Fourier transformation, it's more than 1 million. So what you can, by this simple scheme, you see the more complex the mathematical function is, the more transistors you have to use on this binary encoding. And the question now is, what is the better compute density? Well, it depends on the mathematical function. What I have to add is, what you already see is, so the more complex the function, the more chip space is used, and the more transistors that are involved, the more energy is consumed. So that's the simple law of the digital world. In the analog world, it's different. So in the analog photonic world, a single optical element can already represent a Fourier transform, compensating for 1 million of transistors. And this is in the end where the advantage comes from. The more complex the function is, the more likely it gets that an optical analog computer is way more efficient to compute on those functions. And this is in the end the door opener, because in the past, also from a mathematical point of view, highly needed complex function have not been utilized in the digital world as the cost function was too extreme. We just ignored them. With this new technology, this is the door opener, because now we basically get access to a broad range of mathematical functions that allow us to perform calculation much more elegant than they could be computed in the past. And this is where, in the end, the boost of performance comes from, and at the same time, the reduction of energy.
So you are CEO of Q.ANT company. So Q.ANT photonic NPU has been described as a game changer for AI inference. So inference tasks. So can you tell us more? So can you walk us through some of the key benefits?
Yes, I can. And before I'm going directly to the heart, let me quickly introduce you to the scaling metric of native processing units, because there are 3. The first one is the chip on its own. We can scale the dimensions of the chip. We can scale the number of optical elements. We can scale the wavelengths, and we can scale the clock frequency. So this is the chip. This is what you would probably also be used beside scaling the wavelengths from the electrical counterpart. The second one is the arithmetic scaling, the meaning which analog function I'm using on the elements. And this to me is the most promising scaling parameter, because as already mentioned in the introduction, if we manage to get even higher complex functions to be operated in the analog world, this is where the most boost in terms of performance and energy saving comes from. And the last one then is when you go on how to program these chips, you can also optimize on the algorithms that you then finally are going to deploy on this new architecture. Now, understanding these 3 elements, what we have been using for so far were the first 2. So we were scaling the chip parameters and we were optimizing on the arithmetics. And with this 2 optimization parameters, we already could demonstrate that it's possible to get a factor of 30, not percentage, factor of 30 in energy savings on the so-called AI inference. So whenever you basically type something into your prompt and get a response from the network, there we gained a factor of 30 in contrast to conventional graphic cards, which is the starting point. We are going to work to increase this. But I think for a starting point, this is quite remarkable. And just because we were basically looking at the same problem with a complete different view. By the way, if I may, AI inference was the starting point. We have started also to look into AI training. And what we found, to me, is pretty remarkable. So up to now, you're scaling in the AI training and network by getting more and more parameters, or you basically increase your network depth.
Okay.
Due to this analog computing functions, we now can also turn the last knob in this element, which is the transfer function. It's basically the function that brings you from one parameter to the next layer. This has been so far more or less a constant. And with this analog approach, we now can start tuning and optimizing on these analog transfer functions. And what this showed, for instance, as a first result on training of pictures, that in the like-for-like comparison with graphic cards, we could reduce the number of parameters by a factor of 50, gaining the same results. And this shows that this new way of thinking, this basically getting the true mathematical world into the computing architecture, is leveraging this technology, and ultimately is going to bring the boost for the high-performance computer centers.
So let's talk about the thin film lithium niobate that plays an important role in your technology. So what makes this material so important, so unique for light-based processing? So what challenges did you face in developing, designing and integrating this material into your technology?
Well, now we basically focusing just on the chip. And to me, the use of thin film lithium niobate is the game changer to realize photonic computers. And the reason for this is thin film lithium niobate. I mean, lithium niobate on its own is a very well accepted material in the optical world. It's heavily used in the datacom. The difference here and the unique point is that only a very thin layer on top of a silicon wafer. And this thin layer contains now all the light-related computational tasks. Thin film lithium niobate allows us to control the light very efficient without the need of energy on the chip. We only need a voltage change, in order to encode the information into light, and this up to several gigahertz. This is the big game changer because in contrast to all the other materials that have been used to realize a photonic processing unit, they were relying on electricity, and electricity always goes hand in hand with at least some heat that is absorbed by the material. And as soon as you get heat on your device on the chip level, then you have heat spread, and this causes that you're getting more and more, that you're losing continuously the control over the precise parameters of light. And this in the end was the game changer when we finally realized our thin film lithium niobate technology. To give you a bit of an idea, we're developing this material system now for 6 years. And we started at the wafer. We developed this special type of wafers on our own. We perfectionized it to the extreme. And once we had this, we started to optimize on the lithographical processes in order to write our dedicated photonic chips.
So let's talk more in terms of applications. So you mentioned AI inference. So what other industries or applications do you see would benefit the most from photonic computing in the next years?
Besides AI inference, I already mentioned that we have made very promising progress also for the AI training. because now we are finally able to use very powerful but complex nonlinear functions in a highly efficient way for these transfer functions. In addition, what we also see very good advancement for is, for instance, for picture generation or voice recognition based on AI networks. And on a complete separate stream, what we're currently exploring are physics simulation. So, for example, first results indicate that we have advancements by this technology, for instance, for the simulation of fluid dynamics, as we now can natively calculate Navier-Stokes equations on this architecture. This is, as I must mention, this is everything in a very early stage, but the first results we are getting are looking very promising, and we always gain advantages compared to the digital world. But the extremeness, I would say, it varies from problem to problem. And this is what we are currently building up. What are the use cases where we gain most from? And so far, as I said, the AI training looks highly promising, as well as the physics simulation, especially when it can be simulated using functions like sine, cosine, exponential functions, and so on. So heavy nonlinear functions, which are rather cost intensive to calculate on a CMOS technology.
So let's focus in terms of the ability to run photonic NPUs in current infrastructure. So how seamless is the integration of photonic processors into data center, in today's data centers? And just talking about data centers, so how do you see also the broader market responding to the growing need for sustainable technology solutions with particular regard data centers as well?
First of all, I see this technology as a co-processing unit. It's not the one-stop shop for everything. We're going to see CPUs and GPUs in the future as well, and we need them because native computing units can't do everything, but they can certain jobs much better than existing digital counterparts. So, and this already points towards the integration, and this is what we pursue at Q.ANT. We want to get this technology as minimal invasive into this ecosystem as possible, meaning that per definition, we're using the standard interfaces of this industry. May it be Ethernet, may it be PCI Express, may it, you name it. So the interfaces are the standards. And in terms of code structures, it's exactly the same. From my belief, the programmers of the world should not have to change their source code. So they keep their source code as it is currently. We take care about a compiler extension that's then available with this hardware. And the ultimate thing the programmers of the world need to do is to recompile their code and then execute it on a combined chiplet structure, which consists out of a CPU, a GPU, and an NPU.
Nice technology, nice future for photonic computing. So, Michael, just last one. In conclusion, so moving forward, looking ahead, what are the next from your company? What are the next major milestones for Q.ANT and photonic computing as a whole?
Currently, we are preparing to launch a first product based on this technology, which I assume is available by beginning of next year. You're going to hear about this pretty soon. In parallel, we are looking so much forward to it. And in parallel, of course, we make progress on the chip architecture itself. We are preparing for the next chip generation. And in what ultimately is still currently in the development is that we get the first libraries, which then can be used by the open source community to start working with this new technology. So this essentially are the 3 steps that we are currently prepping for.
All right. So Thanks a lot for joining us at Embedded Edge, Michael. So see you next and talk soon. Thank you.
Thank you.
That brings us to the end of this episode. Stay tuned with more news and technical aspects about embedded technologies. If you are listening to this on the podcast page at etimes.com or embedded.com, links to articles on topics we have discussed are shown on this page. Embedded Edge is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.